Chemical reactions don't just happen, they're the result of molecules colliding. The more often they collide, the faster the reaction could go. But not every collision leads to a reaction. In this video, we'll explore what affects the frequency of collisions and what it takes to make them count. We'll use a kid's playground game to help make sense of it. This is Real Chem. Collisions drive chemical reactions, but what actually controls how often they happen and whether they lead to a reaction? It comes down to three key ideas: how frequently molecules collide, their orientation during collision, and the energy of the collision. Let's break it down and explore the science. First, let's consider how often molecules collide with each other. We can break this down with an analogy to a kid's game. Imagine a playground where every kid except one has a flag tucked into their back pocket. The kid without a flag is it, and their goal is to steal one from another kid, making that kid the new it. Now, here's the twist. In our game, all the kids, including the it kid, are blindfolded and moving around randomly. They aren't chasing each other intentionally, they're just wandering and bumping into each other by chance. This is sort of like how molecules move. They don't have a plan, they simply collide randomly. If we pack more blindfolded kids into the playground, the it kid is going to bump into others more often. More collisions, more chances to steal a flag. The game speeds up. Similarly, increasing molecular concentration, like crowding the playground, leads to more collisions per second, speeding up the reaction. So concentration matters a lot. But it's not just about collisions, because not every collision leads to a reaction. Just like on our playground, where not every bump results in a stolen flag. So what does it take for a collision to succeed? Well, another key factor is orientation. In our game, flags are in back pockets, so the it kid has to grab them from behind. Bumping into someone face first won't work. Similar situations can arise with molecules. Take bromomethane reacting with hydroxide ion. For a reaction to occur, the hydroxide ion must collide with this side of the bromomethane. If it collides from the other side, it just bounces off the bromine atom, and the reaction is unsuccessful. But even with the right orientation, a collision won't always lead to a reaction. It also needs enough energy. Let's go back to the playground and think about a different game: football. In a football game, it's not enough to just collide with someone, you must hit them with enough force to knock them down. Molecules are sort of similar. Collisions need enough energy for the reaction to occur. We call that energy the activation energy. But unlike football players, molecules don't knock each other down when they react. Instead, the collisions that are energetic enough rearrange the chemical bonds, transforming reactants into products. Here's how chemists envision the role of activation energy in this rearrangement of bonds. The y-axis represents energy, and the x-axis shows the progress of a reaction in which the reactants have the right orientation. For our reaction, this means breaking the carbon-bromine bond while forming a new carbon-oxygen bond. As these bonds rearrange, the energy of the system rises, reaching a peak. If the collision has enough energy to push us over this peak, the reaction succeeds, and the reactants convert to products: bromide and methanol. This peak represents the activation energy. That's the minimum energy needed for a collision to lead to a successful reaction. So the rate of a reaction depends on three things: the concentration of reactant molecules, which determines how often they collide, how many of those collisions have the right orientation, and how many have enough energy to get over the activation barrier. That's the key to understanding what makes reactions fast or slow. By thinking about reactions as molecular collisions, we can understand why some happen quickly, some take their time, and some don't happen at all. Keep these ideas in mind, and you'll start seeing reaction rates as more than just numbers. They're a reflection of what's happening at the molecular level.